Welcome to my YouTube channel. In this video we are going to be solving some problems involving friction using the Newton's third law of motion. So the first problem we are going to be looking at is for this system. So we have a system and we have this problem to be solved. So we are asked to find the least force needed to set this body at a constant speed, to set it moving at a constant speed. So the mass of this, or the weight of this, is 1.5 Newton. The weight of this is 3.5 Newton. And the coefficient of sliding friction for these two surfaces and these two surfaces is 0.45. So to solve this problem, we first of all consider this system, the first block. So for this first block, we notice that the string is attached to the wall, and once this one is set on motion, this particular block will be stationary. And what that means is that the tension in the string must be equal to the friction opposing this motion. So because of that, we have the tension in this string minus the frictional force, which we call F1. The frictional force in this place must be equal to 0 since this block is not moving. So with that, we have T equal to F1. And remember, your F1 is also known as mu s capital letter mu times r, right? So let's consider the second block. For this second block, we have F moving in this direction. Then we have two forces opposing it, one from this side and another one from this side. So mathematically it can be written as F equal to F1 plus F2. And since we know that this block is moving at a constant speed, F1 minus F minus F1 minus F2 should be equal to 0. So if you take this one to the other side, that gives us F equal to F1 plus F2, right? So as long as it's not accelerating, then it's not equal to ma. So now that we have this, right, then we notice that our F1 is mu times r. This one is also mu times r. So let's see, mu s, where this one is the coefficient of sliding friction. So mu s r1, mu s r2, right? So we can factorize mu s out, and that gives us this expression. Our r1 for this system is the weight of this first block, while our r2 is the weight of this block and this block, because the friction here is as a result of this entire block, which is r2. So we have r1 becomes w1, r2 is a combination of w1 and w2, right? So if you combine these two, you have mu s 2w1 plus w2. Since we are asked to find the least force needed to set this system at a constant speed, our F is to be determined, mu s is known, these parameters are known, so we have 0.45 from here, then 2 times 1.5 of the smaller block, this one is the bigger block, then we have 0.45 into this one, and we have 0.45 times 6.5, and at the end when you multiply we get the final result, which is 2.925 Newton. That's it. So let's look at the second problem, problem 2. This problem 2 also looks like the other one, but a little bit different. So we have this system, and let's see the problem, or what we're asked to look for. So we're asked to find the least force that can set the bigger block in motion at constant speed. Thus this time around is the same force needed to set this one at constant speed, but this time around is a string attached to this one and also attached to this. But this time around we're told that the weight of the first smaller block is w1 and the larger block has weight W2 equal to 2W1. That this one is twice the weight of this one. So to start, we resolve this first one, this first block. So we notice that there is a tension in this string pulling in this direction, and there is a frictional force moving in this direction. So let's see the mathematical expression for that system 1. We have T minus F1 equal to 0, then T equal to F1, and remember that our F1, which is the frictional force, is equal to mu r. So this is how we express it. T equal to F1 equal to mu s r1. This one is the sliding coefficient of the sliding friction. R1, which is equal to mu s W1, which is this weight here. Right? Okay, so we'll move on to the next one, which is the second equation for this one. For this expression, we notice that this force here is opposed by 3 different forces. So we'll consider the first one, which is this one here, the frictional force between this surface and this surface, which is opposite. We also have the tension, then we also have the frictional force between this and this block. So there are 3 forces opposing this particular one. So that's why we have F equal to this. And because this one is set at a constant speed, that's why we have F, which is supposed to be minus T minus F1 minus F2 equal to 0. We now have all this one move to the other side to be equal to this expression. But notice that we have already found the T to be equal to F1, because the T in this string also goes round and it's still the same T in the string, the same tension. So our T will be replaced by what? F1. So we have F equal to F1 plus F1 plus F2. And if we combine these two, we have F equal to 2F1 plus F2. Now, what is our F1? Mu R1. What is our F2? Mu R2. So we have 2 mu s R1 plus mu s R2. So we can factorize mu s out, and we have mu s 2R1 plus R2. We have already seen that our R1, which is the reaction, is equal to the weight for the smaller block, while R2, which is the reaction, is equal to the weight of the smaller block plus the bigger block together, and that gives us 2 R1 equal to W1 plus R2 is W1 plus W2, right? So we can combine these two, and that gives us mu s 3W1 plus W2. From this point, we also notice that W2 is twice the block of the smaller block, so that gives us 2W1. And with this, if you combine this and this, you have 5W1. If we rearrange, we have F equal to 5 mu s W1. So we can see that this F can be found in terms of what? Our smaller mass W1. And once this particular parameter is given and this one is given, you can always find it. So that's it. Thank you for watching. Please like, share and subscribe to this channel. Thank you.